You were hearing, nobody was hearing this. Thank you, so thank you. You say me 5 minutes, so speaking along with a couple of guys here. I will go back again. Sorry for my 4 minutes watching me doing nothing. My name is Guillermo, and I will discussing these days about programming in Fortran. Can you hear me now? Yes. So we will try to do this far more interactively. So I will know immediately if you are listening or not. Are you listening? Please, someone. Yeah. Okay. Thank you. So this will be 4 days about Fortran. Fortran is the language of choice for scientific computing, for what is called high performance computing. The other two languages, hardcore, are C and C++. But Fortran is the language that has been used for years for weather modeling, for nuclear reactors, for fusion nuclear reactors, for material science, density functional theory. Most of those codes are written in Fortran. For astrophysics, for basically most of those areas. In chemistry, molecular dynamics. If you search Amber, NAMD, GROMACS, most of those languages are written, most of those codes are written in Fortran. Again, same thing for the density functional theory. Fortran is the language of choice. Fortran has been around for more than 60 years, from a date that predates the existence of computers as we have now, with keyboards and screens. Computers back then, if you search on internet, they have a nice videos where they have the machines that feed the punch cards. So you program actually making holes on some cards, and you put those cards in a machine, and the machine will read those cards and after execute the code and produce the output on a printer or something like that. So is that all this language? Many things that you see today on Python, on Julia, on C, were first developed or appear in a language like Fortran. Fortran is especially good describing arrays, matrices, operating with them in a very efficient and clean expression for this kind of operations. So it's heavily targeted toward numerical computing, matrix computations. And also it's a language that have evolved since those days when all that you have for programming was a dumb BP100 terminal. That is basically a tiny little monitor that usually it varies. It used to be greenish or yellowish, orange screen where you program and you only have 80 lines, 80 columns for characters. So you have to put all the code in those 80 columns. And some things from that date were the origin of some of the original restrictions for Fortran. That's no longer the case. So in this course, I will show Fortran, how you program Fortran today. I will try to skip. I will mention some of those things that is still you see in codes. You will recognize when someone still writes the super outdated double precision or real star A or things like that, that you should not be using today. The nuances of programming in Fortran today. And that's some of the challenges too, that this language has been for so long that if you search on internet, there is some web page which show you how to do something in a very outdated way. So I will skip all that and show you how those things, how the standard works today, especially 2003. There are multiple standards, so what I will be focusing in what is Fortran 2003, 2008, and 2018. What else? So I cannot pretend that you will learn Fortran in 2 hours. But what I will be doing is to introduce the language in the first hour, kind of a revision of best practices, modern ways in the second hour. And you will really learn on the third hour. Are the exercises that I prepare for exploring the specific size of the language, where you will really learn. So the way that I expect you to see this is that during the first hour, you basically absorb the index, how things are presented, where they are, but you will not learn during that hour. You will not learn during the second hour. It's less than an index, it's more like a bunch of different topics scattered in the second hour. It's the third hour where I will be here, listen to you, the struggles, I think, where you will actually learn. So how much you will learn, it depends on you, on your previous experience with other languages. If you're really, really new to programming, you will be able to do some of those exercises, but we'll have to skip some others. That will be the mark. I will present some things that are kind of advanced, like overloading of operators. I don't expect to go that far. I will skip some of the things, some of example things that are through 2018 Fortran, like core arrays or things like that. I will show a little bit tomorrow about that. But I will go into a more classic exposition of the language today. The way that the text, the narrative, at least for the first hour, is prepared, is that we will learn in a constructive way. So when you're learning a language, from the index point of view, is building bottom up. So you'll start learning about the letters of the language. And the accents. After that, you will learn about the words of the language. And after, you learn about how to make sentences. And after, how you make paragraphs. Same thing here, how you type text for Fortran, which are the words that are used in Fortran, how you make statements that are equivalent to sentences, how you write procedures, functions, and modules, which are the equivalent of paragraphs or entire chapters or books on a natural language. But that's not how you learn to speak a language. You don't learn to speak a language, learning the letter, learning the words, and reading the dictionary. So that's why the way you learn this is during the exercises where you will explore this material that I will be presenting today for actually programming something. For the next days, we will be discussing mostly about parallel programming. The general overview about parallel programming, OpenMP, third day about OpenACC, and fourth day about MPI. What I expect is everything that is needed for the next 3 days, for day 2, 3, and 4, is what we will be presenting today in the first hour, plus the specific topic of the parallel programming paradigm. So now that we have many people, we have 12. Okay, so we cross the line of that. So what about if you tell me if you have experience programming in Fortran? You can say yes a bit or not. The idea is, I don't expect most of you to actually end up programming in Fortran, but at least this is a good time for you to learn reading Fortran, because sometimes you will face an issue with the code, and being able to read and understand what the code is doing could help you to solve the problem yourself or guide the developers on where is the problem with that code, and that facilitates finding a solution for it. So I will appreciate if you just type on the chat if you are here for the reading side of this, or you have experience programming, and that will help me because most of you are remote. To see how fast I will go on certain topics, or if I go slowly, even if I sacrifice the last part. So please feel free to type your experience in Fortran. So, as I told you, Fortran have evolved have been created for more than 60 years ago. And okay, even if you are new to Fortran, you can learn some things from other languages, from Python, for example. So Python actually took NumPy, took a lot of things for the way you manage arrays from Fortran, the way you expand the slices and the slicing procedures in NumPy, we actually took from Fortran. So you can pick things here and there. So there are some milestones in Fortran. So to get an idea, Fortran was created by IBM back in the 50s, 60s. As I told you, machines those days doesn't look like a computer today. And the language evolved, part side, IBM from a scientific point of view, but also with input from the US military, who actually enforced some routines from DARPA, and they introduced some things that end up in what is called Fortran 77. Fortran 77 was the big milestone in Fortran back then. Even though some of the things were not ready at that time for Fortran 77, so the military introduced a couple of things that were actually standardized a little bit after that. But that was called the standard Fortran. And it was very stable. Nobody changed that in more than 10 years until they come up with the Fortran 90. And Fortran 90 was the next biggest step that introduced dynamic arrays and things like that. A more flexible way of programming was the next thing. And at that moment, even though it was a nice milestone, not many compilers, free compilers were available. So many people still continue to use Fortran 77 because that was free at that time. Fortran 90 compilers were expensive. So even during the 90s, many people continued to program in Fortran 77. And after some of the things were fixed or were cleaned during Fortran 95. So 95 was a small improvement or cleaning up on top of Fortran 90. And after the big jump was Fortran 2003 that introduced more elements, modern elements that we will see today, standardized on procedures, command line, interaction with the operating system, binding with Cs, things like that. And the last iterations of this are 2008 and 2018. There are not many things in 2018. There are still some things that still are not implemented in modern compilers because this is really new. But 2008, most compilers today, most of the modern compilers support this. So that's okay. So the first part here is learning to compile a Fortran code. And by the way, if you execute this, let's see, let me see. Oh, we can do this. Oh. Okay, I will show you in a minute which is the command that I have. And so, in the meantime, first go and connect to the cluster. It's you don't remember here we have we have instructions for doing so. So how to connect to the cluster? This is the web page. I will copy and paste this on the chat. So here on this web page, you will see instructions for connecting to Thorniplan. So please do that. In the meantime, I will see to show you how to download the materials. So I will paste the command. So here, if you want, I have here the examples. All the code that you see on the web page is right here in the sections. So here I have, for example, this first example, and I try to mark those so you can check the codes there if you want to. And it's right here. You execute the commands here, and all the files are available there. So let's go first here. So the first thing that we will do is something very classic, is like an introduction to this, is understanding how a Fortran code looks like and how you can compile this code. So what we are doing here is using a function, and we are using Quaternions here for integrating this function, which will return pi over 4. So this is a way of computing pi via integration. And the integration will be splitting this domain uniformly with tiny little rectangles, and summing all those rectangles together to compute pi over 4, and of course pi as a consequence of that. So this is what we are doing. Basically, we are converting this integral into a summation, and this code is doing just that. This is a Fortran code for doing that. So how we compile? We have, and I will demonstrate this with 4 different compilers. We have the GCC, and I have 11.1. This is one here. We have the Nvidia compilers, and we have the Intel compilers, the 2021. Those are the most recent compilers on all those 3 vendors. And this is exactly what we will be doing here. So again, let me review a little bit what we have. We will see this in detail later on. A program, a Fortran code looks like this. Start with something like program, end up with something end program. Later, we will add more things beyond this, like subroutines, functions, modules. But a very minimal code will have at least this program, end program, and inside we will have some lines. Those lines have specific meanings. Each line is in general a statement that will produce an effect. The spaces here are not important. You can space more or less this, so you can even put this in a long line, and it's still up to a point. There is a limit on the number of columns in Fortran, but still you can make continuation lines. We will see all that. The code is printing something, is doing a loop. I am setting the color like because I'm using VR. So if you are using Nano, I unfortunately think you will not. Let me see how that looks with Nano. With Nano, the only thing that is with some color is none. I don't know why, but so Nano will not color this. Let me see Emacs. Emacs will color it. So it understands Fortran syntax. Let me see MC edit. And MC edit will also color this somehow. So yes, that's why I'm getting the colors. So is the editor who is able to recognize the language, the syntax of the, at least some words and associate special words in the language with a certain code. That's why, which is very, very good, very, very handy when you are programming. It helps readability of this. It makes things easier. And so that's why. So I'm doing a loop here, and so I'm doing several things here. I'm doing this summation, this summatory encoding is written here. And after that, some printing on that. So we will see all that in detail. But it's good to have a first exposure to this. So let's compile it. Let's compile it with something. Let's start with the lang module load. Lang, oh, not this one. GCC 11. This is our first comp. This is the GCC. This is the GNU compiler collection. That's the meaning of GCC. And the compiler in this case is called Fortran. So we compile these examples for 0, and we hit enter. So you can go and execute the clone, clone this repository, go into files. So after you go into Modern Fortran, you go inside files, inside Fortran, and now you can compile this. So when you compile it this way, this is the simplest way of compiling a Fortran code. Just Fortran and the name of the file, the source file. And if you do that and everything was fine, you will get this executable. And you can execute this. Another way of doing this is if you want to declare a name for the resulting executable, this is the way you do it. So put a name, it doesn't need to match, or it could be whatever word you want. And at that moment, the executable will be this. If you have the name, so example, it will be exactly this. So this is how you compile with Fortran, with the GCC Fortran compiler. Now, next compiler is the lang Nvidia Hpc. So this one is the Nvidia Hpc 21.3. That's the actual version. In this case, by the way, in the Nvidia, this is the new name actually for the Nvidia compiler, is NV Fortran. And the origin of this compiler for Nvidia comes from the PGI, the Portland Group compilers. That company was bought by Nvidia a few years ago, and very recently they changed from the usual PG Fortran that used to be the name for the compiler for this, into the NV Fortran. So that's what I will be using, the NV Fortran, and I will do exactly the same, compiling the code and executing the code. Okay, so this is how you compile the code with the Nvidia Fortran compiler. And finally, this is how you compile the code with the Intel compiler. It's called compiler 121. So this is how you load the Intel compilers, the most recent version, the 2021 version of the Intel compiler. And the name of the compilers in this case is i4. So i4 example 0090. And same way, the code executes the result. Okay, so that is what we have here. On the web page, you will see that here I loaded 3 compilers in one single line, and I was compiling the code, all 3, in the most simple. And all of them will produce a.out executable But if you want, you can change the name of the executable for a different one. The output will be something like this, and you will see that it's different with different compilers. We will understand why it's different. So now you know how this looks like, how you compile it. So all the examples here are here in this folder. So 001. So when we move into each example, you can go and open and change and explore a little bit and compile by yourself and see what is going, what those codes are doing. So this is how we learn this. This is how you could learn a language, programming language. You don't learn a language taking a book and reading the book from one cover to another and you learn that. No, that's not how that works. You need to know an index. You need to know a structure of the language. And after you start, you need to solve problems with that language. That's how you learn. And that's why the exercises are targeted for that purpose. So the idea is to force you to go back here, everything that we will say in the next 20 minutes, and review where it is. So that's the idea. Try to keep where are those things mentioned in this text, because you will need that for the exercise. And we are constructing this from the bottom to the top. So how you program, how you write a code in Fortran. You use the 26 characters of English by default. You put some language allow you to put strings in UTF-8, but you cannot do like in Julia that you can put a smiley face like a variable. That kind of things are not possible in Fortran. Only in Julia, as far as I know. In the old times, people wrote codes in uppercase, in full uppercase. That's kind of ugly by today's standards. So from time to time, you will see still codes that are written that way. But those are from the old Fortran 77 style. Today, usually a good style is writing in lowercase. It's easy to read. And you can put in uppercase things like that. Things that go beyond the language, like the directives that you will learn tomorrow about OpenMP, for example, are good things to put in uppercase to make them visible. Things like preprocessor directives, things like that could go uppercase. But it's not mandatory. If you want to program in uppercase, it's okay. One thing to know is that Fortran doesn't distinguish those things. If you run program or you write entire code in uppercase or lowercase, it's exactly the same. It will not pay attention to those things. So now, the next structure are certain tokens, certain words that are here and there that have a special meaning for the language. So end, program, block, procedure, function, all those things that are tokens. There is something special with Fortran. There are not reserved words like in Python or on other language. Things that you cannot use, for example, for variables and for naming variables, and we will see that. So in Fortran, you can name a function, or program, or things like that. And it's possible. It's not the best way of programming, and you can make the code far more confusing by doing that, but it's perfectly okay from the technical point of view. There is a limitation of 132 columns in the program. And if you need more, you need if the line goes beyond that, you need to use continuation lines. And continuation lines are with the ampersand. And here there's an example of how you use an ampersand, for example, for making a long line that extends beyond the 132 characters. So this is a line with actually 132 characters from here to here. So this is the limit. This is the actual limit for it. And before, the limit was around here, but that was relaxed up to here. And you can put continuation lines, as I show you here. And continuation line, if you really, really want to stick this with the next line, and here I'm writing pi with an absurd number of decimals. You need to use ampersand here and here, and that will stick the lines as if they were part of the same thing. You can put comments in Fortran loops like this. And you can even insert comments in the middle of those continuation lines. It's okay. By the way, this is example 001 for those we are looking into the codes. And you can make a very, very long lines like this. Yes. You can also put several statements on a single line using semicolons. But you should only use this for very, very short statements like this. It's a really, really bad idea from the style point of view or readability point of view to put the statements in a sequence, long statements in a row. So not good style. Now, those are the rules for the words, for the tokens. What else? Oh, now, the next thing, types. In Fortran, there are 5 types, 5 intrinsic types. And we will explore those in the terms of constants, and later we will discuss about variables. So here I'm mixing a little bit those concepts. But a constant is just the number, You type the number, that's a constant. A variable is a name that you are putting to a constant in the space in memory that you can change. And even a more global way of doing that is putting a name to something. And that name could be a constant. So we will see that with some attributes, we can make a variable not variable. So types. There are 5 intrinsic types: character, integer, real, logical, and complex. Beyond that, what you can do are derived types. There are constructions that cluster intrinsic types together for making something that makes sense as a group. So we will discuss the possibilities for all those types, for all those 5 intrinsic types, and now how you make derived types. So integer. On a computer, usually integers are represented with 32 bits. There is no restriction on the language to be like that. So using 32 bits, this is the range of numbers that you can represent with signed integers. But again, the language itself doesn't force to do that, to be like that. The modern way of controlling the precision or the number or the range of those values is by using an intrinsic function that returns an tag that identifies which is the kind or the flavor of the variable that you have to use, or the kind for the type that you need to store a certain value. So let's go into this in detail, because this is one of the confusing things in Fortran that are hidden in other languages like Python are not so hidden in Julia. In Julia, you will be exposed more directly to these kind of things. But in Fortran, this is important. By default, if you don't care too much, you can declare something to be an integer. Will be an integer up. It will represent some numbers up to in a certain range. But if you want to be sure that you can represent every single integer with 6 digits, so from minus 1 million up to 1 million until 999,999, you need to declare a variable that will store a value and use that for declaring, for example, constants, integer, that are integers of that kind. So 2 concepts here. One is the type, another is the kind. And the same type will have several kinds. The Fortran language asks for at least 1 and at least 2 types for reals. And we will see for reals, for example. Reals are a little bit more complicated because with an integer, you are storing in 32 bits. So you are basically putting zeros and ones, 32 sets of zeros and ones that are able to represent up to this in this range here. With real numbers, with floating point numbers, it's a little bit more complex because you have basically 2 things. You have the amount of decimals in the binary representation of decimals and the exponent. And different standards, you can decide, okay, I need more digits for the decimals, and I will sacrifice some digits for the exponent. Or I can put more digits for the exponent and sacrifice some digits for the decimals. And it's still using 32 bits or 64 bits. And the language also doesn't force any specific representation for those. But there are ways here to declare that you want a real that is able to hold 99 decimals in precision and up to 10 to 99 in 10 to minus 99 up to 99 or so to represent 99 for the decimal exponent, not for the binary exponent of exponent, by the decimal exponent. And with that variable created, which is an integer, so this number, this is an integer. You can create constants with that kind, with that type, real, and that kind, R9. So that's the name that I put, R9. So that's how you represent those numbers. And this small code, I don't know if I wrote this code here. Probably they don't have an equivalent in this. It's too small. I am making a small example with this. So I am asking for this number. And I am showing the kind, the precision, and the range. So this will provide me the kind that I need to store a number with 9 decimals, 9 good decimals, and up to 10 to 99 in the range. So this is something. In the old times, back in Fortran 9, there is something that people use, real star 8 and double precision. They are considered obsolete. They are still valid, so not truly obsolete. They are something that you should not use. As I say, discourage its usage because there are better ways to represent. When you say double precision is double of what? There is nothing except if you want to attach to a specific IEEE standard that declares how you spread 64 bits or a certain number of bits for the decimal part or the exponent part. So it's double of what? Also, some people use, or some compilers used to have the kind to be an integer that reflects the number of bytes. So they put kind equal 4, kind equal 8. Those things are not standard, even if some people use that way, because Fortran and all the 3 compilers follow the same thing. There is nothing in the language that enforces that kind of thing. So this is the right way of doing it. Okay, so here I have a small example of a continuation line for a character. So this is how you write characters. No, before that, complex. Complex numbers are pretty much very similar to reals. They also have kinds. Basically, it's similar to the kind that you associate to the real, but notice that we are storing a complex, so then the number of bytes that you need to store this number is the double of a real number. So 2 numbers involved. So the next type is character, and here we are talking about literals. So there are 2 ways of writing a literal in Fortran, with double quotes or single quotes. There is no difference between double quotes and single quotes as existing, for example, Bash programming, which makes a difference about this. And it's similar to the way Python, for example, interpret those things, that you can change, you can change between double quotes and single quotes, and you can use the single quotes because that help you to write double quotes help you to write single quotes inside without escaping those. And same thing for double quotes when you want to, you put them inside a single quote literal. Same thing for expanding here. Oh, by the way, those graph, this is one example that these kind of things will not work. Let's say the grave AdSense are not permitted, are not. And this is something that happens sometimes when you are copying code from a web page and you paste it on the terminal and end up with those AdSense that and after the code will not compile. So pay attention to those, that those are not accepted in the language. And the final intrinsic type is logical, and they receive values true and false. And they also have types. So believe it or not, the language accepts that you have multiple kinds for logical. Okay, so now names. Fortran is extremely flexible in how you name something for variables and things like that. And just for make you an example here, and the coloring is because the system is becoming confused about that. But there is nothing that prevents you from naming a variable program or real or print or something. You can use words that you associate to the language for creating variables. It's a really bad idea to do that. But it's something that you can do. So don't do it, but know that there is nothing that prevents you from doing that. And usually, a good style means that you stick with something like this, like underscore for multi-word variables or things like that. Or sometimes, with a more modern flavor, you can go for a camel case like this, where each word starts with uppercase. And this is something that eventually you can use if you are more in like object-oriented programming, where this is very customary. But I will be using this for this. So I will be using underscores. It offers a good start. Okay. Usually try to avoid name for variables. This is a style. This is just experience that tell you something that is a good idea or bad idea. Don't name a variable E, J, K, M just with one letter, except if it's something that is in a loop or something that is really stupid, really dummy. Put variables that mean something to you, that have some meaning, that you can associate human meaning to them. Not only because you understand what this code is, that variable is storing, but also because it's easy to search. When you are searching in which place you are using a certain variable, if you put a variable with just one letter, you will get the entire code being highlighted because the letter is everywhere. So this is a good idea to do. Variables. So this is how you declare a variable with certain kinds. And here on purpose, I put this way that is very common, but it's actually it's not a standard. It's not a mistake, but it's not a standard. So it doesn't guarantee that this will work on any Fortran compiler. Putting kind equal 4. There is nothing in the language standard that says that 4 means something. Or 8 means something. Or that number even exists as a kind. So this is not a good idea. But at least the 3 compilers that we will be using today, they have the same meaning for this. So that's something that you know. Here, the variables have, this is the type, this is the intrinsic type, this is the kind, and all have the same thing. Except character, which could be a string, and in that case, apart from the kind, you associate a length. So how many characters you have on that string. And after the one way, it's okay. No, that's late. No, that's not the meaning. So imagine that in Fortran, in Intel Fortran, and in the Nvidia Fortran, kind equal 4 exists, and it means, for example, integers that uses 4 bytes for storing the number. But there are compilers, there is one, if you search on internet, there is one, and I think the predecessor of Fortran, which is, well, it was G95 or something like that, use 1, 2, we was using 1, 2, and 3, I think. So 1 was 16 bits, 2 was 32 bits, and 3 was 64 bits. So they use a different number. So this is not a standard. The point is, this is not a standard. Kind equal 4. If you want to use it properly, you should be using something like this, real kind, or something like integer kind, something like this. And you will get a number that is the right number for that compiler that allow you to produce numbers that are capable to store 6 digits. And that's the right way of writing a code in Fortran. If you don't care too much, the numbers will not be close to that limit or something. You just put integer and that will be okay. But if you want to be very, very precise, this is the way you do it. Declaring asking for the right kind and using that kind here. You will see that in a code. This is just for remember me for mentioning this to you about the non-standard kinds in Fortran. And this is a very simple. I will be using this because I will not end in all nuances for printing in Python and Fortran because it's kind of complicated. And doing this. Now, derived types. Now, we have now 5 types, 5 intrinsic types. And now we can group those types into package that has some meaning for the code. And this is a small example of that. This is a derived type that I call Adam. And this atom has inside another derived type that is called position. And this derived type here has 3 numbers, so 3 real numbers. So I'm using one derived type inside another derived type. So to build in this thing here, I'm trying to avoid words that have some meaning in programming languages. So they give you a structure, but I will be using the structure in a different sense. When you create an instance of that, I am creating a structure. So gold is a structure of the derived type atom, and I am initializing that with this constructor. So just putting all the initial values in the same order as they were declared here will create this structure gold with all the information inside. So this is how you build derived types. And this is how you use those derived types. And this is really, really important when we move into object programming, which is, I don't think that we will go that far, definitely not by the time. And that's how you go inside the different sections of a given structure. So here for this goal, if you want to ask for the atom name, this is the percentage is how you go deeper into the into there. Yes, you are right. Like, the kind could be different for different compilers, or could be unexistent in one compiler. And that's something that actually can show you here in this example. This is something. Look at this. Just to clarify this situation with. The code was the same. The code that I show you was the same. But notice that here, kind was 16. For Fortran was 16. For the Nvidia Fortran compiler, the maximal it produced was 8. Was 8 for this. So this one was capable of a precision of 33 decimals and up to this. And here it was capable of only up to 307. So this one, MV Fortran, is not, it will not go to the next level. And the Intel compiler produced the same thing as the Fortran. So the same range, the same precision, but not this one. So pay attention to those, that those are not standard. I was asking on this code, for example, which was the maximal kind that I could produce to go up to 33 decimals of precision. And the Nvidia compiler could not go that far, so it moved to the next one, was this one. So different compilers will have this different information, and this is something, when you are really, really doing numerical computation, this is something that is relevant for really precise calculations. What else? And so, okay, so this is a type constructor here. And this is how you select a component selectors, how you go deeper into an element. A complex number is not a derived type, but you still can use the percentage to go into the real and imaginary part of the complex number. So this is like kind of an exception, at least for that type, that you can access the real and imaginary part. So now, another thing that you can build with those intrinsic types are arrays. Arrays are collections of elements that are of the same type and same kind. So when you build an array with integers, all those numbers are integers, and all of them have exactly the same kind. And that's one thing. Another thing is that an array have several elements. The dimension, so it could have 2 dimensions, 3 dimensions. In this case, we have 2 dimensions here. And they have also a extent, a rank. So which are the values that are stored along each dimension? And the indices, the limits that were used for declaring those numbers inside those arrays. This is different, for example, compared, for example, to Python. In Python, the arrays start from 0. Same thing for C. In C, arrays start from 0. In Fortran, arrays start by default from 1, but you can decide from the limits of that. You can start from -10 to 10, and the indexes will be from -10 to 10. So that could make easier arranging arrays somehow. So the code will arrange the limits. It will go for the right positions in memory for you. That's one thing. So you can have arrays of multiple dimensions. By default, they start by 1. The maximum limit for an array is 15 dimensions. And 15 dimension is quite large. Imagine that if you have 15 dimensions, you cannot store more than 10 elements of each dimension. More than 10 elements and you hit 1 petabyte of data. So 15 is quite a lot. What else? Another thing, this is important. In Fortran, the elements, okay. In general, the elements will try to be contiguous in memory, following the internal index. So then the element that comes after A11 is A21, and after A31, and after it moves to the next, to the second. When it exhausts the internal index, which is moved faster, it goes to the next index. And that is here, the second, number 2, 1, 2, 3, and after 1, 2, 3. So it's the first index, the internal index that moves faster. This is the opposite from C. And that has a consequence when you are programming, for example, moving a loop, that you should pay attention which is the index that you are moving in the internal loop compared with the external loop, because there are an important performance issue if you interchange the indices in those double loops. So the continuity, they are contiguous, or they try to be contiguous there. When I say they try to be contiguous, I mean that the array not necessarily will be on the stack. So when you declare arrays in Fortran, they usually go in a spatial portion of memory that is called the stack. That is relatively small, and the cluster is like, I think it's 8 megabytes. If you go beyond that, the code will crash. And we will see this in a minute when we move into the next section. So let's keep it like this. So constructor for arrays, there are 2 ways here. This is the old way, and this one is the new way. Pick whatever you want. It's not actually obsolete. It's just a little bit more verbose. You have to make 2 symbols. But this one is clean, and it's probably easier if you come from Python, and this resembles a little bit more than this notation that is quite old. So you can use those. And also you can use something that resembles, it's not as powerful as the Python list comprehensions, but you can make arrays, make an array implicitly with a loop by doing this. So this with the notation, whatever the notation you put in place. And here we are making an array where you are filling with A, starting with the number 2 up to 16 with jumps of 2. So this is something, there is an implicit loop happening here. And this is perfectly okay in Fortran. Now, one of the big things that appeared with Fortran 9 was this dynamic memory allocation. In the old days, when you need to write a code, you write a code for a certain size, and if the matrix or whatever was bigger, you need to recompile the entire code. So that's what people actually did. And there are still codes that are using this awful way of programming. So you, from time to time, you hit some of those codes that for actually running the program, you need to recompile it every single time. And it's because they are using static arrays. And so the size of the arrays are arranged during compilation time instead of dynamically allocating them. It has been, the solution has been created since the 90s. So, and some people still don't use it. But anyway, the way of doing that for declaring an array that's change size is declaring this way. Real, you declare the dimension, how many dimensions it will have. You can fix the number or you can not. But if you are making something allocable, you just put this column here to say, okay, this will have 2 dimensions, period. And you make it allocable here. So you make a promise that I would like to stick this as much as I want at some point. And here with the word allocate, I can actually make the space for storing the array. In this case, I will put n elements here on the first dimension, and I will make here an array that goes from -m, and imagine the m is a constant that was defined somewhere else, up to m. So it will go from -10 to 10, if that is the value of m. And when you finish with that, you can just deallocate the array, and that's it. Deallocate is not mandatory. It's a good thing to, in some cases, prevent memory leaks. But if you are in a subroutine, the deallocation is automatic. This is not something that people realize or it was clear. So for being safe, it's better always to deallocate those arrays. What else? The strings, they are declared this way, so as I told you. And they are formally different because this is a scalar. Even if this is a string of characters, from the point of view of Fortran, this is a scalar of one string that has 32 characters of length, but it's still a scalar entity of an intrinsic type. And you can create arrays of strings, but that's another thing. Now, pointers. I will not go too deeply into pointers, but this is a nice thing for performance issues, for certain operations. And I actually have one exercise. If you ask me about this, we will discuss this more in depth. Pointers are just locations in memory for variables. So when you declare a pointer, you need to declare what that pointer is pointing to. This is a pointer for an integer, and it will prepare some information associated with what is called a descriptor for having the location of memory of something that will be an integer, another variable that will be. This is how you declare that with the attribute pointer. And it could be a scalar. So this is a variable that contains the position in memory of another variable. And in this case, a scalar. But it could be also a pointer to an array. And this is a pointer to an array. And those things will have different content inside. So that's why it's important to declare which is the type, and also if it's the dimension of what you are pointing to. The pointer when it's created is in an undefined position. You don't know if it's pointing to something. You can make the pointing in a more defined state by nullifying the pointer. So a pointer that points nothing, which is different from a pointer that we don't know what that is pointing to. Those are nuances, but okay. Anyway, this is how you nullify a pointer, or this is another way for pointers. But we will really not enter into it. They'll make it really crisp. So now we are in just the words. Variables, literals, so constant, literals, and variables. So those are the words of the language. Now, the next step, once you know words, is how you make sentence out of those words. And those are expressions and statements. Yes? Because it needs to know if you are pointing to an integer or you are pointing to a real number. So it needs to know, for example, if that is, let's say here, this pointer, PA, is something that can point something only to an array that is real and has 2 dimensions. So the system needs to know when you are sending this, for example, as an argument for a function, that you are sending something that actually is what you promised to be. Let's say, imagine that a function is asking for an integer. You are sending a pointer. If the pointer doesn't, you don't say a pointer to what, the compiler will become confused. This guy is sending me a position of memory of what? What should I expect this position of memory? So that's why, even if it seems like pointless, it's a position of memory. So imagine that it should be just a bunch of bits for something in memory. It needs to know, and it's in the descriptor, which are this variable pointing to, or which is the kind of variable that this is pointing to. That's why you declare it that way. Okay, expressions. So now we have 2 elements in the language: words and variables. So imagine in my metaphor, a variable is something like dog. Okay? A dog. The dog could be a dog. It could be this dog, or this dog. A constant is a particular instance of a dog. Is this that is right here. And now we will be operating with those things, with the variables and constants. We do this through statements or expressions. And this, for example, is summation. We are adding variable b with the constant or literal 5 and storing the information of that inside C. So there are 2 things here. One is taking the location of memory, where is b, taking 5, making the sum, storing that in C. You can, this in particular, for example, this is an operator, and this operator is a dyadic operator. So it needs 2 elements, the left side and the right side. There are operators, for example, like minus, that could have just the right side. It's just the number, and if it's -5, it's just take the number and get the inverse in addition. So that is called a monadic operator. So, and after that, you can have like successions of operand, operator, operand, operator, operand, operator. So how they work? They work from left to right in most cases, except for exponents. Exponent is kind of an exception to that, but otherwise it will be this way. So it's A divided by B, and after divided by C, and after divided by D. The compiler could change that, could realize that a division is more expensive than multiplication, and rearrange that during compile time and do this. But that will be the compiler trying to optimize things. If you put it this way explicitly, the compiler will follow this prescription. If you put parentheses, the compiler will follow the parentheses. If you don't put the parentheses, even if it's the same thing, putting this way, it's exactly the same thing. But there are reasons why eventually you want to force this operation, especially if you are dealing, for example, with numbers to extreme values. And you could lose precision if you are doing divisions for very small numbers, and after very small numbers, and after multiplying for a very big number. And it's better if you arrange that so the numbers don't go too far, where precision becomes diluted. So there are reasons for arranging that for numerical accuracy and also for optimization reasons. Okay, and exponents, as I told you, is an exception for this. So in this case, it's b times b raised to c, and after that, a raised to that. So it goes backwards, but that's how that works. That is the exception. Also, if you put literals, 12 divided by 3, it will be equal to 4. 14 divided by 3 equals 4. So they will return an integer. This was the way that Python did back in Python 2 point something. And now Python 3, for example, does differently. If you put the integers, it returns real numbers, floating point numbers. But Fortran does this in the old way. So pay attention to that. So usually what you want is to convert the number before doing operation. And the way you convert that number is with these functions, conversion functions. This is for converting something into an integer, something into a real number, or something into a complex number. And it's something that we will see in a few examples. I think that I put it on the first example when I explicitly convert the number into real, or I just put a real literal explicitly, because otherwise I will be getting something like this, returning integers where I don't want those. Now, operators, more operators. This kind of operators returns true or false, and they are let's say, relatively well known if you are born in other languages, except this one. This one is slightly different. In other languages, it's with an exclamation mark, but in Fortran is /equal. This is the modern way of typing those. Wow, before they have .gt or something like that. I will not. But you know that on all codes, you will find something like that, GT, LE or something, .LE or something. Those are more operators for logical, for booleans, not monadic, and this, or equivalent, or equivalent, okay. So those we will be using in a minute. Array expressions. So this is how you declare a variable that will be an array with a predefined dimension and range, a two-dimensional array and one-dimensional array. So notice that we have double columns here. So all the attributes come here first and after. So the type, eventually in parentheses the kind, and after in comma you will put all the attributes. And after double columns and then list of variables that you want. That's the modern notation for this. And after you can do those operations. So in Fortran, you can do a lot of things that are implicit loops with arrays, and they work nicely. So you can, for example, divide A divided by B. Imagine that you populate this, and it will do element by element division of those elements. You can take an array and add a constant. So the constant, you can imagine that is promoted like an array of the same dimension of B, and after you will make a summation element by element. So Fortran will be able to do that. Also, you can take slices and pick, for example, this is a vector. So this is a one-dimension array here that will have 10 elements. And here I have a slice here, a section of an array here, also with 10 elements, and I can sum those implicitly. And here, this will return true if every single element in all arrays are returned as equal. So many things in Fortran can be done without looping. Contrary, for example, to C. C is not a language originally for scientific computing. So when you are doing this kind of things, you have to use loops somehow, or external libraries that hide that, put that under curtains. Now, controls. We will go into the most basic controls here, all that you use in general are if, conditionals, and do loops. So that is what really matters. New things. Here, you can put a name to a conditional. You can put a tag. And after you can do things that you need to be careful, but it's possible to ask the code to go into a name loop. It's something that is discouraged in most cases. It could make the code hard to read, but the Fortran still has, and sometimes people use it, go-tos, it's okay. But that should go like a very end or an exception or something. Like it should be a tail of a code, a go-to. But yes, in Fortran you can put a name to a loop, to a condition. This is how the conditional will looks like. One condition, something, some statements, another condition, more statements, default condition, if nothing happens else, will go somewhere else. And this is how you close the condition. This is the more general one. If you want to do something really packed, for example, something really small, something in Python exists, this kind of things too, is something like this, in one line, one condition and the statement, and that's it. So, the case, this one, it's similar to the if, but in this case, it will just go for one case, one evaluation, instead of this one that will produce multiple evaluations. So there are reasons why you want to prefer this one instead of this one. But also this one could cover ranges. So it will cover ranges, all the elements up to -1, for example, will do something case 0, or all the elements starting from 3 will go and do something else. And there is a default case also that you can insert. Not so commonly used, but I put it there. So I don't think that you will need it for the exercise. The do loop is really, really important in Fortran. We will be using this a lot. This is one example for a matrix multiplication. There is one exercise for this. So you can copy and paste or use it. Pay attention. So we are taking a matrix n times k times k times m matrix, making the multiplication. So a triple loop. Not the most efficient way of doing that. And there is an intrinsic for that. And also there are libraries specialized on doing this, both for dense matrices or for sparse matrices. So this is the dummy way of them. But it's a nice way to show a do loop. And this is a small example of how you can exit from a loop. A loop will repeat an operation over and over. And there are ways of either skip one particular case. So this is an exception, but I don't want to abandon the loop. I want just to continue on the next iteration. You use the cycle word, the cycle keyword. And if you just want to abandon entirely the loop, you use the exit loop, the exit statement here. You can use both. And there is one way, I think that I will put it in the next section, where you can have multiple loops nested, and you can go from one inside loop and exit entirely from the outer loop by using this naming. Well, I never did it, but the same thing that I did for the if, you can name loops and you can exit from the loop. We will see this. Now, programs. Now, the next part is, once you know the lines, only know the sentences, the next thing is paragraphs. Paragraphs and chapters, books. In this metaphor, a paragraph is a procedure. So a set of statements that you execute together as an entity that makes sense. And they follow an order, they follow a narrative. This is how this looks. We saw this from the first program. It looks like this. Program starts like this for program. Some statements, some variable definitions, some statements, and program. This is how you write a program. All programs in the exercise will have the same description. This is the most minimal. I didn't want it to do it for the first, but this is the most minimal program that you can imagine. Program, print this, fine. Programs will have some elements that you want to repeat them or you want to put them aside so you can call them as a separate thing. And there are two kinds of those subprograms in Fortran. One are called subroutines, another are called functions. This is kind of unusual because in Python, for example, there is not such distinction between functions and programs and subroutines. A function, let's start from a function. A function is something that is expected to just return something at the end. But typically, it's not supposed, a pure function is not supposed to change the arguments in any way. So the arguments are read-only, like in a mathematical concept of a function. You receive something as an argument for the function, and you return something else, right? A subroutine is something that doesn't return anything, but eventually could modify whatever you enter as arguments for it. In this case, for example, this is a subroutine, and I am declaring here explicitly. You don't have to, but this is a good style to declare that something is just for input. I will not modify this variable. This other variable here, x, is also the intent for this variable is for input. I'm not supposed to modify this variable. If I try to modify this variable inside the subroutine, I will get an error during compilation time, which is good because I will be realizing that I'm modifying something that I'm not supposed to modify. And this variable is something that will serve only for output. So I will never use whatever it is in that variable. If I try to use it during the subroutine, it will throw an error because the variable is just for output. So this is good for programming, putting the intent of arguments in a subroutine. And a subroutine needs a call. You need to put a call something when you call it, when you are calling the subroutine. You will see that. A function on the other side is something that will do nothing with P1 and P2. Those are pure input. Will do some operation and return something. One way of doing this is to put, probably, yeah, there is a typo here. Here should be distance 3D. Here, this is a typo. Typically, the name, you can change that. It's not mandatory to be like that way. You can put return here and return a different variable. But usually is a variable with the same name as the function. So here I should enter distance 3D here. And here I'm doing an operation with a loop. And at the end, the function will return the content of distance 3D. That is how you write a function. And a function could be part of an expression. You can take this function plus this function, but you cannot do that with subroutines. That's why Fortran makes a difference between subroutines and pure functions. Now, input and output. The easiest way, and I will input and output, formatted input and, yes, not need to be the same, but if not, you can put it here, return this. The return, so here I could keep this and I could return in parentheses distance. That's my point. This is Fortran. In Fortran, if you don't want to put here return after here, this variable should be called distance 3D. And whatever it is at the end, it will be the return of the function. Oh, okay. So now, input and output. Input and output in Fortran could become really, really complicated. There are a lot of ways of reading files in different ways. I'm talking about reading and output from files and also from the screen. Reading from the screen or writing into the standard output or standard error. If you don't want to complicate the life, and I will not do this in this introductory exposition of Fortran, this is one way of doing it. You put a star. The star is, I don't care about formatting. Those are the variables that I want. So this is on a string, var1. And after a variable, put that variable, you figure it out how you want to put it. Another variable and another variable. Another string, another variable. This is a very simple way of doing it. It will be enough for the exercises, and the time is running short on this. And now, this is Fortran 2003. Back in the 90s, all codes, most codes that were written in Fortran they never read anything from the command line because there was not a standard way of doing it. That changed in 2003, where they introduced a standard in the language, in the standard, a way of reading from the command line. And this is a small example on how you can read the number of arguments that you enter on the code. So this is example 10. So I will actually show you here. The example 10. So here I am getting the number of arguments that I would get. And here I'm making a loop showing you those arguments and the length of those. So let me see. G Fortran, example 10. So if I execute it this way, I will say number of arguments, nothing. But I can put 123, 45, something like this. I will get 3 arguments and I will be able to capture those and do something with that, which is handy. Another way of doing this is with those read. I don't think that I make an example for a read. Read from the keyboard. It's actually a bad idea to program that way. Okay. So that was introduced in 2003, and there is no reason 20 years later not be using something that has become a standard. See. Oh. Okay. Oh yeah. Here I'm doing this something. Data. So here I'm reading on. Oh no, here I'm converting numbers. So here I'm reading whatever it is. Okay, yeah. So here I am reading these numbers. When you read the numbers, they become strings originally. And if you want to convert them into real numbers or integer numbers, you can use the read, let me see, like this. The read function here to convert this string into an integer or real number or whatever you want. And after I returning those numbers back into the code. And I have just 20 minutes for something that's supposed to be like 1 hour. So let's move quickly into this. I don't think that I have too much time to go into all those elements, but I will go into some of them at least. So all Fortran used to be uppercase everything. You don't need to do that anymore. Free format. Originally, you search on internet or very old Fortran, you will see the first 6 characters being empty or having some kind of weird C in some places, a number in column 6 or things like that. This is really old-fashioned Fortran, 77 or before that. And so they separate the first 6 characters like controls, and that dates back when you program in by making holes on a code. That is no longer the case. You should not be doing that. So now you type normal, lowercase, from the very beginning, from the first line, everything is fine. So this is a small example when I'm showing that. By the way, all those examples are here in advance here. So all the examples that I have here, you can go compile, explore how they were created. Is like here. What else is here? Okay, this is style. It's a good idea to make some indentation, especially it's not forced by the language like Python is, but it's a good style. You can decide 3 spaces, 4 spaces, but do something that help you to read that the code. If you need the continuation line for some reason, use the ampersand. After the ampersand, you can still use a comment. It's not a problem, and the code will continue here. It's perfectly okay. So okay, this is a better style. So separation, some lines, so the code becomes more visible, more readable. You understand this code quicker. All style do loops. So this is the really old style from something like this. Separations, uppercase, things like that. Forget about that. A better code will be something like this, lowercase. By the way, use this. I think I will mention this implicit num. By default, I, J, K, N, M were integers by default. All those were integers. Everything else were real. That could become confusing because it assumes that the variables exist and things like that, and they have a specific type and kind. So it's better to put implicit num. In most cases, it's better to put implicit num and explicitly declare all the variables that you need on the code, so you know what to expect from it. It depends. You are asking about indentation in VR. I think that I have it, but I disabled today. I have it because I install like a set of packages for coloring, indentation, correction, things like that when you program in Fortran. That's one thing. So I think if you have a plain VI, it will probably not work as you expect. The indentation will be weird or will make 8, or they will not realize that. You need to install some packages. You search on Google, for example, on the browser, something like that, for VI, highlight or indentation or formatting for VI, Fortran VI. And you will see some packages, and you can install those packages on your own account, and you can use them for that. And there is also something. There is one. I was using this a lot. So there is this. Well, for this, module load. It's a Python thing. It's Python. It's something that I installed. Python, C, Python, something, GCC. Yeah, and it's called Hpc. All right, this one. I install it. You can install it, but what it does is basically it makes all the indentation for you. So I was typing quickly, so I was not paying too much attention about the indentation. I type all those examples by myself, so it takes some time, and you just write quickly the example line, just need that to work. And after I run the Hpc, and the code will nicely indentate it. And those are very small examples, so it's really quick to make the right indentation for that. So search for it, and there is a nice package around for indentation. That variable attributes. We mentioned those in the first section, in the first hour. So they mentioned allocable pointer. We never mentioned target. Some arguments. So this is something I mentioned either. In modern Fortran, some arguments, for example, you can make them optional. The same thing that happens, for example, in Python. Some arguments, if you don't put them, it's okay. It will assume a by default value. And you can ask if something, you can declare that something is optional, and after you can ask inside the subroutine if the code was present, if the variable was present or not in the command line. So all this set of our attributes for variables, use them. But we mentioned some of them, but there are not. In particular, dimension and allocable. They are really, really important. Try always to use allocable arrays, not fixed array. Some people, what they do or they used to do is to make an array that is big enough to be sure that the arrays that you will be using will fit. This is okay, but there are better ways of doing that. So declaring always an array of 1,000 elements, even if you, most of the time you will be using just 100. It's not a good idea, even if you have a lot of memory. And so here is a small example of those attributes. I put here an example. This parameter, for example, I never mentioned, is for making constants. So constants that are constants inside the language. That is different from the constants that you can create with preprocessor definitions. This is another thing. So those are constants, and you can treat them as constants. So you can create here an array directly with the size n, and it will work. So parameter, dimension, allocable. I use that. So I create the array here. I populate the array, and I bring. That's it. Implicit none. Use it all the time. Otherwise, these variables, if you don't use this, these variables are integers. Everything else are real. For the small codes or for the small loops, it makes sense eventually to skip that and make an example without the implicit none and make the code smaller. But when you are really writing a serious code, you should always impose yourself an implicit none. Also help you to debug. If you make a typo and put the variable with something with a slightly different name, and not that you put an uppercase or lowercase, but you make the name slightly different, as I did. Dimension 3D, and you mix that, it will immediately pop up the mistake. Loops, I mentioned that you can abandon the loop with exit, or you can just skip one iteration with cycle. Is right here, this option. And here is an example of this. If I reach here, I'm making a loop for here for the cosinus and sinus, and if I hit something where the value makes explodes, I am here exiting from the loop. And here I am doing exactly the same, but instead of just abandoning the loop, I am just cycling. I just skipping. Please consider this is example 5 and example 6. So compile those and check the difference by yourself between those two. It's exactly the same code, except that I'm skipping the loop instead of skipping one cycle on the loop instead of abandoning the loop altogether. This is a nice example. I think that this is not part of any code real, but this is how you can name a loop, put a tag to this loop, for an outer and inner. And from the inner loop, I am abandoning the outer loop. If I don't put this exit, I don't put this outer here, it will just abandoning the internal loop. But this is a nice way of, for those nests, loops from abandoning the external one directly. Or same thing, cycling, so skipping up to the next outer. And the case construct, we discussed a little bit this, is different from the C. If you are familiar from the C case, that looks very similar, but in C, it makes all the evaluations. It will go from this one. If this passes, it will go to the next one. It will also always will explore all the cases. So for that reason, typically in C, you have a break. You always have a break to abandon, not exploring more cases. In Fortran, you don't have to put a break because you always evaluate just once in the case. So that is for people who is familiar with other languages. The kind of variables, okay, this is those are, for example, in Fortran, you can use this intrinsic module. This is a module that is part of Fortran 2003. It's part of the standard 2003, and we have this constants, these literals here, constants here, that will return all the kinds for that particular compiler and for that particular type. So this is what I got for Fortran, for Fortran. For Fortran, they have 5 versions of logical kind. I don't know what is the meaning of having the extra ones, but that's what they have. And they have 2 types of character, maybe because they are able to use something like UTF-16 or UTF-8 for characters. So those will go with a different kind. That's what I imagine. Integers in Fortran, you have all those. And in the case of integers, and in the case of Fortran, the number means the number of bytes used to store that number. This is particular for Fortran. So they have 1 for 1 byte, 2 byte, 4 byte. By default is this one. 8 bytes, integers or long and extra long integers. And they have 4 kinds for real. So 4, 8, 10, and 16. And this is kind of unusual. Only Fortran, I was checking other compilers, and only Fortran has this kind. So if you want a number that I think has 33 or 32 digits, something like that, it will go for this kind instead of going for this kind, and it spares a few bytes. So pay attention to this. And here is an example, and this one is actually example 8. I will actually execute this one. Being example 08. So this one is this code here. So basically, I am making you, getting you an example where I am using all the kinds for the integers and these all versions of real. So here I am declaring this old-fashioned real 4, real 8, double precision. All those are old-fashioned ways of declaring. And this one is back from Fortran 66. You should not be using those kind of things anymore. And this is the new way. So with the actual real kinds and that. So, and after that, I am asking for the kinds that those codes are using, and exposing the number of digits, significant digits, in decimal significant digits that I have for them. And basically I'm evaluating here the square root using those numbers, using numbers for those precision with different kinds. So this is like a summary of all this kind of things. So I compile that, and this is what I get. So this real, those are different concepts. One thing is that the processor is having like 16 lanes on the process. Imagine that you are in a highway, and the highway has 4 lanes. It doesn't mean that you can still pass 8 cars from those 4 lanes. It's just that only 4 cars will pass at the same time. But you still can process numbers with 128 bits. It's still possible. And actually, there are libraries where you can work with arbitrarily large, specialized libraries where you can work with arbitrarily large integers. You can declare an integer with 1,000 bits, and they will be able to process those bits. It will internally be processing those with chunks and making the algorithm to work with them, but it's okay. So this is what I'm getting. Double precision here, 8. Real times 8. So those are the kind that I'm getting returned when I'm using that. But notice that here, I can use, and I put it here, I can put some flags here during compilation time where I can switch or I can increase the number of bytes used by certain kinds. So if I compile this way, with this, like this. So let me see, let me do it this. Okay. So here is what I got when I compiled it this way. Now I am promoting everything that was declared real. It will be a real with 16 bits. And I execute it. And notice that this kind for a real, during compilation time, it becomes a 16 byte real. And notice here that I was making the square root, and now I get a lot of decimals from that because those numbers were declared that. Same thing for the double precision. So now real and double precision became the same thing. So it's double of what? So when you compile, it's something that you can do if you want, for example, to catch. If you are having numerical issues, it's something that you can do quickly for a special routine and promote those reals into 16 to see if that is having an effect on numerics. That's something that you can do. And at that moment, you are promoting reals into 16-bit. But those that were declared with kind will be preserved. Notice that nothing changed here in this. This is still like this. This is Chi9. This thing that I declared with Chi9 is still 8. And the number is like this. And here I have some other things. Some other ways to compile. So adding more things. The double precision, I wanted to just the double precision to be 8. So the double precision will be 8, but by default, everything will be 16. So I can change and I can mix and match, and I can change those things during compilation time. The Intel compilers have, I think, similar ways of manipulate those things. The functions are different. The arguments here for the compilation line are different, but there are ways to tweak those. So pay attention to that. The best way of, let's say, serious codes is having like a configure file where you declare the precisions with kinds very precisely and use those globally in all the, in the entire code. So now, 2008, this is Fortran 2008. Add some standard definitions for real numbers. Real 32, real 64, real 128. So some compilers will have real 128. G-Fortran is one of those, for example, that give you that. If real 128 doesn't exist, it will return -1. That's the case, for example, for the Nvidia compiler. The Nvidia compiler is not capable to representing those, so it will be using those. And so this is something that you can try, for example, try to compile this with Nvidia. And I think the code, well, I never did. Yes, but the Nvidia compiler will not be able to get a value for this. If it's, they will return -1. It means that it's not able to represent. And now you don't have that issue. Arrays, so examples of declaring those arrays are here. When you need it for the exercise, you can pick one of the examples and familiarize with that. Now this one is kind of interesting. I will mention that. When you declare an array with a fixed dimension, fixed size, some compilers will try to put that array on the heap, on the stack. This is small size memory that usually has some limitations. It's limited by the operating system to be like 8 megabytes or something like that. You can force during compilation to move all the arrays into heap. And at that moment, you will not have that issue. That is something that happens with some codes where they ask for raising the stack, and I will show you that. So how you see the limits of that? Okay. So okay, all the limits. So the system has what are called limits for a variety of things. And one of those is this, the stack size. So we can concentrate on this, the stack size, which is in kilobytes. So this is 8 megabytes. So it will not be able to put, one process is not able to store more than 8 megabytes on the stack. We have, let me see, what is the H. This is the soft limit, and this is the hard limit. You as user can change that and make this unlimited. So for this terminal, this mode. So that is something that you can change. But I prepare one example, and it's in this one here. Yeah, this example. It's example number 12, where depending on how you compile it, and in the case, for example, of the G-Fortran compiler, you can send all the arrays into the stack, forcing them to fit there, or crash if the size is too large. So this is something for you to do if you want. It will, if you compile this way. Let me see if I can execute it. I think I can execute this. Yeah. You execute this and you get a segmentation. It's because it tries to put the array on a stack. The stack is limited to 8 megabytes, but this is quite a big array, and it will go out. It will not be able to be allocated there. It will crash. There are ways to force that, or to force the opposite, to And here, I probably don't have time. You have the description here, how you can monitor how much of the stack has been used. And eventually, here, a procedure for skipping that. I never put, there is another way for Intel compilers, but I forgot to put it here. Where you can put the array directly on the stack. G4, by the way, Fortran, I think for allocatable arrays, they will always go to the heap, so you don't have that problem. That way, this is a way of forcing it. But the Intel compilers, I think up to a limit, will put it on the heap, on the stack, and that's why from time to time you have issues with the Intel compilers crashing because you hit the stack limit. And some derived types, I think I will skip this. Well, this is like a representation of those, how you move, you ask. So this is an expansion of the add-on case that I showed before. Functional subroutines, here is one example of that. Of an example or subroutine that I create here. There are two ways of doing this. You put it here, or you put it inside the program after the word contains, right here. So you type contains and inside the routine. So it will be routines that are visible only inside the program. But there is a better way. It's using modules. A module is something that is quite interesting. It's how it's just getting into the way of object-oriented programming. You put data types, so derived types, together with some functions in a single package. In a single package, and that package is called a module. And after you can import that module with the word use, the same thing that I'm using here, an intrinsic module, that will bring me a lot of functionality into my code by importing this. So if you have something that has some functions, has some subroutines, has some variables, and some derived types, I can pack all those together and create a module with some subroutines here. And after here, use those inside my code in a coherent way. And there are ways to move beyond that and declare some of those subroutines private. So they can only be used inside the module, but they are not exposed to the outside. Same thing for variables and things like that. This is far from what I can go today, but pick this example because there is one exercise that uses this. This is another example of a module with some public and private elements. So this is exactly what I was telling you then, how you declare those. And here in the program, I am using the module here and getting information directly from the function. The functions were defined here. Okay, some of them you can declare them protected, so they are visible, but you cannot change those inside inside of the program. Inside the program, they are constants from outside, even if they are not from inside the model. So there are more things, optional arguments, and yes, and well, the C part I can skip. So let's go into exercise. We have like 45 minutes, okay. For the exercises today, we have some that doesn't require you to type. So if you go and read and pay attention to what we said about names, the literals, yeah, one first exercise is to identify which of those are not valid. Has some errors there. So those are kind of easy things. So which are valid literals or not. And some of them are relatively tricky. but yeah. So those are no coding. No. Now, this one is before making a program, write a definition for a real number that is able to go from, for complex elements, from range minus 100 to 100. So 10 to minus 100 up to 10 to 1. This is an array. So make the array, make the constructor for this. Okay, so write the constructor for that with an implicit loop. Same thing here, a derived type for a classical point where you have mass, you have charge, you have position, and you have velocity. So make a derived type that is good for containing that information, which is good, for example, if you're thinking about molecular dynamics and you want to do something like that. What is the kind of derived type that is good for that? This is a real with large precision. So try this one. And now we see some problems. So pick whatever you feel comfortable, you feel challenging. If someone is too easy for you, move to the next one. I have a variety. I don't think that you will have time for making all of them. But for example, this one is reading, you can create random numbers, so an array of random numbers. By the way, I think that I have it here. I have it in the previous section. Random, otherwise I will show you how you write, you put random numbers here. Ask me the question. If it's not in the text, probably skip it. And compute the center of mass, or all those variables. So it's relatively easy. It's just playing with the array a little bit. This one is for computing the potential of the Lennard-Jones. Again, this is moving into molecular dynamics, and the simplest case of a potential is a pair potential, so it will be something like this. And if you prefer just the gravitational potential and simulating something like that, or you can change the potential for a gravitational one. The idea is the same. So a bunch of particles subject to a classical potential, and that's it. And a little bit more complex, put the star for that, the hard cases. Start thinking about simple dynamics. So moving the particles along the forces, which will be the gradient of that, and start making the initial lines for ND code. This one is relatively simple, from reading from the command line, or reading or asking for the values of A, B, C, and return the solutions of the quadratic equation. If it's complex, return the complex. Check for zeros here in A, so there is a conditional here that you can use. So this is actually a relatively simple exercise. Here, same thing. You have a bunch of numbers. It could be real, and compute the average, and compute the variance. So the idea is to have a function or have a subroutine. You decide what you want to do, if a subroutine or a function, to compute this, and use that to compute, for example, this one. It's up to you. So here I have some things. So if you get stuck in just tell me the value. This one is interesting. You take just a matrix, you can create a matrix with random numbers, and the idea is to decompose that matrix in two matrices here. And the sum of two matrices. One is symmetric, and another is skew symmetric. Just by doing this, there is one intrinsic function called transpose. So you can use that, or a little bit more challenging, write your own version of a transpose. So if you want to skip the point of the problem of the transposition of a matrix, use the transpose. And the more challenging is all changing that into complex matrices and instead compute the conjugate transpose. And the very simple matrix multiplication, a very simple problem, and compare that with the intrinsic. There is an intrinsic function in Fortran called matbull that will make the matrix multiplication. And there you can also use BLAST or LAPACK for doing it. And one more interesting example is this about quaternions. So we have here this object. It's called a quaternion, has 4 values here that are relevant, and there is a multiplication table for them. So I times I is -1. So it's like an extension of complex. And they have a very specific multiplication table. And the idea is to use overloading operators. So create an interface for it. We didn't have time for talking about interfaces, overloading operators. It's kind of advanced. What I did here is I create a module for it. I created a module for the simple case of the sum. So this is an operator. So now you can create quaternions, A, quaternion B, and you can just, with the operation plus A plus B, and that will work. Same thing, but using this multiplication table, put another interface for the multiplication and make it work. Make it work for the quaternions. It's an interesting, nice problem, it's small still. And test it. The same thing that I did here. I create a quaternion and I put an initialization for them. Another quaternion, and here I have another quaternion Z. I am saying, okay, Z is X plus Y. What I want is X times Y. What happens if you want to program something that is transparently dealing with quaternions, with overlaid operators? This will be a nice session exercise. Pick whatever you want. If you have problems, type on the chat. I can go and check or on a specific problem. And that's it. Tomorrow we'll be talking about parallel programming. That's another thing. Okay. Thank you. Well, my pleasure.
There's a parking thing. Just figure the number that's on the back of the card. If you have it, guess what's the first one. It should be perfect. I forgot to ask you that.
Just in case.
I asked Kelly, she said we're allowed to use them.
Oh, wait, okay.
So, she says it's okay.
So you are not developing the code for the Shiny application. It's already done. It's working.
Yeah, that Brad and